In this video, I wanted to point out to us that there's going to be some similarity between our solubility rules and the rules for what are strong and weak acids and bases. Now, the similarity is not enough to rely on memorizing one in order to know the other. You will need to know these two separately and thoroughly. But I wanted to point this out because it gives us a little bit of an idea of what's going on. And also because if you forget a detail, sometimes you'll be able to regenerate it from the other side. Now, what I've got up here is a summary of our solubility rules, and I've called this from numerous books, so this isn't exactly the same as in our textbook, but it's going to be very similar to what you'll find just anywhere that you look. Things that are soluble are going to be anything that has something from group 1A, anything with an ammonium ion. Then when we switch over to the anionic side, things that have nitrates, these three from the halogens, chloride, bromide, and iodide, and the sulfate ion. And of course, these bottom ones, they have exceptions. So our halogen ions, they will precipitate with silver, lead, and mercury. And sulfate will precipitate with those three as well as Ca2+, Sr2+, and Ba2+. So some of the middle ones from group 2A. Insoluble things are going to be carbonates, sulfides, and phosphates, unless you pair them up with something from group 1A, one of our exceptions up here, and then also the ammonium ion. So these two are the ones that are always soluble. And then our hydroxides. Now this is going to be a critical one because, remember, bases up here. Hydroxides are always insoluble unless paired with something from group 1A, and these three from the middle of group 2A. Now let's take a look at how that connects to some of our strong and weak acid rules and strong and weak base rules. So for a strong acid, notice that we've got HCl, HBr, and HI. These three are going to be H plus paired up with these things that are always able to escape, unless it's a big heavy cation that we have learned here. Well, H plus is a group 1 ion. So it makes sense to us, hopefully, that it's reasonable that these should all be soluble. We get to HNO3, the nitrate ion. That was another one that we said is going to be always soluble. And then our sulfate ion was another one where it was always soluble unless with these big atoms here. So you can see there's a lot of similarities here with the ones that we said are always soluble. So we're thinking of it as being a group 1A that can dissociate easily from its counter ion. That makes kind of sense that group 1A does dissociate well, both when it's a generic acid, a generic metal, or when it's actually H+. For our strong bases, notice the exceptions that we have up here for solubility are going to be our strong bases. So with hydroxide, it's kind of an all or nothing. It either precipitates, like we see right up here, or it's a strong base. So it either dissolves or it doesn't dissolve. Okay, so it dissolves and dissociates or doesn't at all. Now our weak acids. HF is going to be kind of weird because any of our H pluses associated with a halogen were strong acids up here, but HF is weird. HF is kind of so strong that it can't really dissociate, or rather it ends up making a really weird cluster where you'll have, I think it's something like 4 or 5 different HF molecules all associating with each other and making a little cluster. The chemistry of hydrofluoric acid is very strange, and because it's so strange, hydrofluoric acid can stay associated, weak acid, can act like it's a polar molecule and sneak past your body's defenses, where it finally does dissociate, causing deep tissue acid burns, and the fluoride ion can start reacting with your bones. It strengthens your bones, but in the process knocks loose lots of calcium ions, and the calcium ions affect your neurotransmitting system and really lock on your pain nerves. So hydrofluoric acid burns are deep tissue, high damage, high pain burns, and can kill you pretty easily as those things go. Why did I bring all that up? Because it is a weak acid, even though it looks like it would probably be a strong acid, given that strong acids included pretty much the rest of its group. So keep in mind that HF is going to be a little bit weird in a lot of different ways. Our phosphate ion is going to be weak when it's paired up with the H plus ions. Well, we said that it was insoluble. It's really good at keeping things associated with it up here, right? Well, it's also good at keeping H plus associated with it. It can still act as an acid, but it manages to keep the H plus associated well enough that it acts as a weak acid rather than strong. Similar logic with the acetate ion, because if we look up above, actually I don't think I put it into this table, but the acetate ion is one of those other ones where we sometimes have exceptions. So the acetate ion is a weak acid. That's an easy one for us to remember because, vinegar does not act as a strong acid, and this is the active acid instead of vinegar. Now, still, you're going to need to memorize both of these tables, refer back to the book and the tables that are in both, but this should give you some traction for trying to memorize them and spot some similarities between these two sets of tables.